Thank you, Ludmil. Yeah, it's an honor to be speaking here. This title, especially the word prospects, basically means that I don't know how to prove anything. But I'm in good company because about 5-6 years ago, I asked Maxime if he thought he had any ideas of how we might be able to do mirror symmetry and go beyond integers and work with ring spectra, and he said he didn't know. So that was an exceptional answer to receive from Maxime. And so therefore I thought this might be therefore good for somebody else to think about. What I'm going to talk about, we're working on it very actively. There's a long list of collaborators. They will show up during the talk. There are more of them than days of the week, and that's part of the reason why progress is fairly slow. But first, let me explain what are we talking about. So when mirror symmetry started, I was still in elementary school, but it was something that was stated for varieties over Calabi-Yau manifolds over the complex numbers. That's what the string theorists were thinking about. And as things developed mathematically, especially with Maxime's homological mirror symmetry conjecture, which is what this talk is about, one realized that you could work not just over the complex numbers, but over maybe the rational numbers, and in some situations over the integers. And once you can work over the integers, you can also try to ask some questions about finite fields, even though there doesn't seem to be very many natural places where you encounter some very deep phenomenon in finite characteristic that we can formulate using Fukaya categories. Now, what this talk is about is the fact that in the world of stable homotopy theory, there are rings that live on this side. They live over Z. And the way to think about them, the way I think about them, is that one way you can think about the integers is that it's some way of taking signed particles and counting them with signs. So if you have pluses and minuses, they cancel each other, and then in the end you either have a bunch of pluses or a bunch of minuses, so either positive or negative integers. But this process of cancellation was understood in IHES by Tom, probably the first person to have a very deep result on the subject, and that the way that you can formulate it is in terms of Bordism. Okay? So over here, there are some Bordism groups. And what that means is you don't just make them cancel, you really try to think about what is this process through which they cancel. And this process is, in the simplest case, a one-dimensional manifold, which is oriented, that's how you extend the notion of signed particles to one higher dimensions, and it will interpolate between some signed particles on one side and some particle on the other. And now you've done do this with one-dimensional things, but then there are relations among these one-dimensional things which are given by surfaces and so on and so forth for all dimensions. So in some naive sense, what you would have is some Bordism ring, which is a graded group, which records information about Bordisms in all dimensions. Now, it turns out that the notion of signed particles has more than one generalization to higher dimensions. So one of them is what we call the oriented Bordism ring. And that's somehow the simplest one to describe. Actually, I don't want to, yeah. But then there's other versions, and it turns out that there's two of them that are particularly important. One of them is the complex Bordism ring, and the other one, in some sense, the initial one, called the frame Bordism ring. Now, we have some familiar phenomenon in ordinary homological algebra, where it's pretty clear by now that working with graded rings is rarely the correct thing to do unless you have some very special situations of formality. Instead, in ordinary homological algebra, we say you should work with the associated differential graded algebra. You should remember the differentials, you should remember what is causing the relations that produce the non-trivial homology in non-zero degree. And unfortunately, that's not how you deal with these. Okay, it turns out that there is indeed some notion of homology, which is more like homotopy, some notion of relations, which is I just talked about, come from one-dimensional manifolds and so on and so forth. But they're not encoded by differential graded algebra. This is a classical theorem from the 60s. Instead, you really have to work at the level of topological spaces. So these are Bordism rings, but the correct way to think about them actually is to erase these stars, okay, and think about these as actual spaces. So what that means in practice, one way to implement this is you have a vertex for every zero-dimensional manifold, which is either framed or complex, has complex structure or has an orientation. You have an edge for every one of these one-dimensional cobordisms between them. You have a simplex for a two-cell for every Riemann surface, which interpolates between three different possible cobordisms, and so on and so forth. So that you can build an entire topological space. That topological space has some notion of addition, which is just coming from disjoint union, and some notion of multiplication, which is harder to define, which comes from products of manifolds. So they have operations that correspond to addition and multiplication. So the whole thing is completely geometric. It is just the relation of Bordisms between manifold produces a space with these operations, and now if you have the correct framework, you can then think of these as rings in the same way as you think of these as rings. Okay? And the implementations are technical and take a lot of words, but the intuitions are just what I said. So now I can say what the title means. The title means, can we make sense of mirror symmetry over these rings? Now, if I was a different kind of topologist, this is not how I would have started. I would have told you something about spectra and ring spectra and so on and so forth. In reality, these are the ring spectra that existed before any of us existed. Okay? And all the other ones, except for K-theory. K-theory also existed before any of us existed. And all the other ones are just produced by humans, by using tools of ordinary algebra, extensions, localization, whatever, okay? Some kind of algebraic closure from these, okay? But it turns out that in the subject of, mirror symmetry, at least when you try to think about symplectic manifolds, the ones that are produced by algebraic constructions, they again don't appear very naturally. I mean, you can put them in the story later, but at the beginning, this is what needs to be understood if you're trying to think about symplectic manifolds and how the symplectic manifolds and their theory that's associated to these things might be related by mirror symmetry to some kind of B-side. Okay, so that's what this talk is about. Next thing to say is why you might care. So I have a very clear reason why I care. So the reason that I care is because studying some kind of Floer theory with these kind of coefficients in this generalization of Floer theory, which takes into account not just numbers but Bordism, okay, has had non-trivial applications in symplectic topology. I just want to state one theorem. So this is a theorem with McLean and Smith. And I will state it in the way that is maybe most accessible. It says if x over P1 is a smooth projective morphism. Most accessible means I assume there's more algebraic geometers here than symplectic topologists. You can also replace this by Hamiltonian fibration over, x is symplectic. if you want to, weaker assumptions, and x over S2 is Hamiltonian fibration. This implies this. Then the homology of x with z coefficients is isomorphic to the homology of P1 with z coefficients tensor with the homology of the fiber. So rationally, this was proved by Deligne using Hodge theory. The integral statement was not accessible for, this is for 40 years, maybe 50 years, probably. And this is proved using pseudo-holomorphic curves. Which means it's not proved using the Fukaya category. It's proved using kind of the shadow of the Fukaya category that appears to you when you look only at quantum cohomology. But the proof, even though it's a statement about the integers, is actually essentially uses complex cobordisms. In fact, it uses these theories that we produced out of complex cobordism by brute force, that Morava produced out of complex cobordism by brute force. So anyway, so this indicates to me that there's some enormous amount of information in symplectic topology that we can extract by thinking about this higher structure.
So does it mean that this Serre spectral sequence?
Yes, it means the Serre spectral sequence degenerates. But it doesn't just degenerate, like there is an actual splitting that you can produce from geometry. Okay, and in fact, what we can prove is the same thing is true with complex cobordism coefficients. Okay, and then that implies this. It means, for example, this decomposition. You should look at Hertzsprung surfaces. You see, it's not additive. It's not multiplicative. I could switch to cohomology, and then it'll be easier to say. But additively, it's true. But not only that, certain Steenrod operations are respected by this decomposition, and that. The only way that I know how to prove that is to go via complex cobordism. Okay? So this is one A-side motivation. B-side motivation, I don't really have a good one for you. But I want to, to just point out that the question of, taking varieties over FP, for example, and asking whether they have lifts to this world of, again, you can call it spectra, but I would say the world of Bordism, has actually arisen in the subject. So there is a recent theorem of developer. So this is 24, developer. So I will say something non-commutative, and then there's a conjecture. He has a conjecture. He doesn't make it explicit, but I think he probably would know how to prove it if somebody actually asked him to prove it. But anyway, it says if C is a smooth, proper category over, let me just say FP, I think you can probably do this characteristic, which lifts to complex cobordism, okay? Then what he calls the Tate spectral sequence, which I think, there's a reason to not use Maxim's terminology here. Spectral sequence from Hochschild homology of C, double brackets, UU inverse to periodic cyclic homology, P, C, this degenerates. Okay, so this is a statement that Maxime conjectured in characteristic 0. Yes?
You replace the Vickers condition and P1 by P and still get this.
Oh, let's not talk about that right now. I mean, there is subsequent work about this result. If you find this, if you look at the paper that proves this, we only have 2 papers on the archive, and then look at what follows. There is now a lot that follows. People have done this for base Grossmanian and stuff like that. Yeah. Once we showed this, it was pretty clear. You could get quite a lot more. Okay, so this is some theorem that tells you.
What is Tate spectral sequence?
I mean, I think what I wrote is, so this is what Maxime would call this non-commutative Hodge-Duran, but that's probably only a good name for it in characteristic 0. In characteristic P, you have to be very careful, okay? Okay, so This is a statement about non-commutative geometry. Okay, so he has a conjecture. Again, I don't want to put it in his mouth, but I think it's kind of pretty clear that he would conjecture this, that says if X is a variety over Fp, again, smooth and proper, which lifts to complex cobordism, then the Hodge to de Rham spectral sequence degenerates. So this would be homology X with coefficient in. Okay? H to the Rham of X. Okay? So this is, again, it is not explicitly stated in this work. He is a student of Mike Hopkins. I think it's finishing this year. But anyway, so this is the reason that these two things are different is because commutativity in characteristic P is a very subtle property, especially once you start doing this kind of homotopical algebra and thinking about ring spectra. Yeah? So this is, I would say, another motivation for asking this kind of question, because we've been thinking, I mean, at least I've spent a lot of time failing to produce interesting phenomena in characteristic P by thinking about mirror symmetry. Okay? So, and this may explain why this is happening.
Which Hodge to the spectral sequence is this? Is this omega over xp, or is it that?
No, it's so maybe I should just.
It's different omega.
Yeah. So this is sorry. This is yes. This is differential forms.
Over fp.
Yes, over fp. Yeah. And the fundamental for experts, what I want to say is that this kind of result here is, you know, it was due to Deligne and Illuzy with constraints on the dimension of x. Okay.
Is there a conjecture that the quantum moduli exists over there?
I want to make no comments right now about this. So yeah, there's lots of questions we can ask, but I want to move on. Okay. So this is one possible motivation for why you want to ask this. You may want to ask this. Okay. So, one of the things that's pretty clear in this subject, from the, call it the B side, but for stable homotopy theory, is that we have no examples, okay? So if you ask Sanath a question of like, now give me some interesting smooth and proper categories over, you know, Fp which lift to omega u, which lift to complex cobordism, well, he would say, well, this gives you an abstraction, but to have a good ample supply of them, we have no idea. Now I want to point out that, in fact, symplectic topology gives you an abundance of them. So, remark. So if, I don't want to use X anymore, so I'm going to use M, is a Weinstein domain with C1 of M equals 0, then, and now we begin with the part that there's no proofs of anything. So I'm just going to maybe write this in some color to indicate that, you know, everybody, you know, if you think about this, you realize that this must happen, then the Fukaya category of M, I'm going to cite, lifts to complex cobordism as a smooth category. Okay. Now, again, where can you find this proved? Nowhere in the literature, but I can just say fragments of the theory that's necessary to make the statement. This theory appear in, there's some work of Pomerleano, not Pomerleano, what am I saying? Bocelli and Smith, where they basically formulated, they insisted on working, I think, in the frame Bordism case, but they essentially formulated what would be the homotopy category of such a thing, okay? And a thesis of Tim Large at MIT, which unfortunately may never see the light of day.
Can you replace Weinstein domain by some single Lagrangian?
I'm about to. So I don't want to go to the skeleton. Notice here I said yes, absolutely. Yeah. So that I expect you can do. So whatever methods have been developed for doing some micro-local approach to these Fukaya categories, you could try to apply here as well. You know, I think that would be an interesting thing to do. I mean,
Is it Calabi-Yau or?
No.
Yeah. This category is Calabi-Yau. This category is Calabi-Yau.
Okay, so it's Calabi-Yau.
Yeah, but you have to be a little bit.
Yes,
Yes, that's right. So you can. Okay, so again, answer is you can formulate the notion of being Calabi-Yau over Bordism. Okay, it's perfectly legitimate thing to do. Perfectly fine. And it turns out that this category is not only smooth, but it is in fact Calabi-Yau. So I will add that as well to this, and Calabi-Yau. It's actually a delicate question because it will be the case, especially if you don't work over complex Bordism, over frame Bordism, you will have situations where the Fukaya category exists and is smooth over frame Bordism, but is not Calabi-Yau. Okay, that is a phenomenon that occurs. But it's related to questions of the form. You see here I put C1 equals 0, not 2C1 equals 0. If I put 2C1 equals 0, then it would exist and be smooth, but not be Calabi-Yau. We can discuss later.
So where do the Calabi-Yau dimensions take value? Like for over the complex numbers, the Calabi-Yau dimension is an integer.
Yeah, it'll be the same thing here.
It's an integer?
Yeah. It'll be the same integral.
So is this omega, is it a simplicial ring, something like this, technically?
Is it a simplicial ring? No, I don't think you should think of it. No, it's not. No, it is. You shouldn't think. It's not. You shouldn't think of it as a simplicial ring. It's like it has. I mean, I don't know what to tell you. It is. I think of it as a simplicial space, as a simplicial set, which is basically a topological space with, with this kind of structure. I think the point is that simplicial ring has like a stricter notion of commutativity of multiplication than this thing actually has. That's the difference. Commutative multiplication is a bit delicate here.
But this doesn't lead to the omega frame?
No, it does not. In general, it does not. You can ask for which end does this happen, and then I would have to strengthen this condition here significantly. Okay? So now this doesn't, of course, satisfy this because it's not proper. And to get properness, work with what are called partially wrapped categories. Which basically means instead of having this Weinstein domain, you also have some structure on the boundary of this domain that will kind of prevent the flow, prevent you from having infinitely many orbits, and then you will get rid of infiniteness. Okay, and again, the expectation is that this will be smooth category. It is not Calabi-Yau, unfortunately, not anymore. Okay, so again, once the theory is developed, then you will have examples where you can do this. Now, but basically everybody who has thought about mirror symmetry knows that this is some kind of toy case. Okay, the cases in which you can formulate the mirror as something that lives in some Weinstein manifold are basically situations in which you are not like dealing with the deepest questions. So, what is required to do that? So, what about the case of M compact? And here we face some fundamental problem. So the reason this lift exists, okay, is because when we do Floer theory, we study Lagrangians and we study moduli spaces of holomorphic disks with boundary on those Lagrangians, let's say holomorphic polygons. And now those moduli spaces of holomorphic disks, they will be manifolds with corners maybe, and as long as the Lagrangians are sufficiently nice, let's say stably framed, which by the way, the generators that we know, when we prove smoothness of this category, the generators are just disks. So there's no problem there. As long as you assume some nice condition on the Lagrangians, then the moduli spaces will actually have natural stable complex structures. And so therefore will give us We'll have coefficients in this ring, and then that's how the category lifts. That's the basic idea.
Could you remind what is Weinstein domain?
Yes. Weinstein domain. Simplest example. I mean, I won't remind you of the definition, but I would just say the simplest examples are affine algebraic varieties. With the symplectic structure that is induced from restricting the standard symplectic form on Cn. Okay. I'll make a standard. Turns out it doesn't matter how you pick the embedding. In Cn, you'll always get something symplectomorphic. That's what you should have in mind. Of course, there's this more general. It's a Weinstein domain is basically you just do this and you do the Stein version, and then actually that's it. That's all the examples we'll ever see. Okay. So what do you do when M is compact? So the problem, the moduli spaces are not, in general, manifolds. Okay? This is something that was observed a long time ago when Gromov-Witten theory was first set up. But there was a proposal, probably floating in the air for a long time, probably first written down by Joyce. Consider them as derived orbifolds. Okay. So what is a derived orbifold? Well, there's many technical definitions. Simple definition that is reasonable to say in a few words is, i.e., you have some base, some orbifold base, let's call it O. This is some kind of total space, an orbifold. You have some bundle over it, V. This is an orbifold bundle. And you have a section S. And your moduli spaces are described as S inverse of 0. Gives us a structure of the moduli space. If you replace orbifold by manifold, this is not a very useful definition because you can always perturb S up to Bordism so that you perturb S so that you end up with smooth manifold as your zero locus. Then you can just ignore the rest of the data. But so you have to take these things up to equivalence. And equivalence means that you can stabilize. But in the world of orbifolds, there's groups associated to, at every point here, there's some group that is the stabilizer in some sense if you present it locally as a quotient. And that has an associated representation on the tangent space of the orbifold, and there's an associated representation of on the fiber of this orbi bundle. And if those two things are different, you cannot achieve transversality. Okay. So that means that there is an associated Bordism ring. Orbifold. And this was studied by Pardon, who showed that, in some sense, you can think of that Bordism ring as one of these ring spectra. Okay, but he didn't kind of build a multiplication. But anyway, there is an associated. I'm going to put a quote unquote space with addition. Okay. So in some recent work that I posted in the archive with Blumberg in the spring, you can see, if you kind of unwind everything we say, that in fact the derived orbifold Bordism ring is a ring in which you can ask questions of this nature. So there exists. We only proved associative derived orbifold Bordism ring. Okay. That plays the role that kind of that lives under this complex Bordism ring. So what would you therefore expect? Well, so the question therefore becomes, can we make sense of mirror symmetry in the situations where we have compact symplectic manifolds as being defined over this? Make sense of HMS over. Now, first problem, we know very little about this. Very, very little. Among the things we know, one thing we know for sure is that there's a map to Q. Okay? This is the map that everybody uses. If you open some, say any construction of Gromov-Witten theory, there will be a construction of virtual fundamental cycle, and then you'll integrate a bunch of stuff and get numbers out. You'll get numbers here. Okay? They actually will come from something here, and then you will integrate. Okay? So this is the usual VFC. I'm not sure. Maybe I should put Kontsevich mine, but okay. Usual VFC. Okay? So since then, there's been some development.
Are you in the spectral or homological?
Sorry?
HMS theory?
Yes. So I'm saying, exactly, a spectral version of HMS, which is where the coefficients are given by this thing. So, so there was some development which goes under the name of Fukaya or Parker perturbation. I'm going to say Fukaya OP, and really this was done formally by and Xu, which said that in fact there is a map to Z. Okay. So this is kind of very interesting development in the sense that, like, by using techniques of symplectic topology, it actually turns out that if you have this means something like, this is just go here. If you have point mod gamma, you don't actually have to count this as 1 over the cardinality of gamma, which is what you would do here. You can actually just count it as 0 if gamma is non-trivial and 1 otherwise. Okay?
So there is no commutative diagram, it's just two different...
No, they're just 2 different arrows. Okay? But in fact, you could do whatever you want. You could say, this goes to 1 if P divides the cardinality of gamma and 0 otherwise. Okay? You can do whatever you want. There's a lot of flexibility in these homomorphisms. Their multiplicativity was not analyzed very carefully except for one case, the one which is everybody goes to 0 except for the thing that's trivial. But anyway, so this is one thing you know. Another thing you know is that this has a map to K theory.
So sorry, what is the statement that there exists a homomorphism?
Yeah. Let me just say it like that. The homomorphism is constructed geometrically, okay? But for now, let's just say there exists a homomorphism, okay? There is a map to, this is complex K theory.
Can you say what the flexibility is in this FOP thing?
I mean, it seems that the range of choices basically has to do, it's at least as large as, you look at isomorphism classes of finite groups, and then you just look at ring maps from, and then you look some monoid generated by that, and you look at maps from that to Z. So it looks like that's at least as much, and you might be able to get more choices because we don't know the structure of this ring.
But it's just additive homomorphism.
No, this happens to be a ring map. At least one of them is currently known to be a ring map, and the rest of them have not been proved to be. There's at least one. Okay, so there's a map from here to K theory. So unfortunately right now, this is only known on coefficients. So coefficients means when you pass to the underlying graded ring, but every indication is that in fact it will turn out to be true at the level of spectra, but anyway, the level of these ring spectra. And this is basically index theory. Okay, so you can find this, discuss some version of this. You can again extract it from some paper of mine with McLean and Smith. And we explain how classical work of Atiyah and Singer on equivariant index theorems, transversely elliptic operators, okay, will tell you that there is a map from here to here. And again,
is it related to what Sasha Giventel tried to do last year, some these indices of some orbifolds?
Yes, it is. Yes, there's this Kawasaki-Riemann-Roch, which is some relation about how this map and this map might be related to each other. Okay, and then there are other things that we know. that are more mysterious, having to do with some spectra that, again, don't have good names, but they're just produced by algebraic methods. Okay, but I would say kind of beyond this, we know very little about the structure of this. And so I'm going to, this is a theorem in progress. So and this theorem says that this map, which is just the inclusion of manifolds inside orbifolds inside derived orbifolds, I'll write it here, splits as a map of modules. Okay? So this is a ring, this is a ring, this is a ring map. So therefore, this is a module over this. You can formulate all of this in the world of ring spectra, but whatever. There is a splitting. There is a map that goes the other way. Okay? The map that goes the other way respects multiplication by this, but does not necessarily respect multiplication here. Okay? So that leaves a question, of course. You know, I can ask it as a conjecture, but I think that would be really, really bold. But so I'll just ask it as a question, which is, is there a multiplicative splitting? So the statement, our proof of this result, our map is certainly not, our splitting is certainly not multiplicative. And our splitting uses, in an essential way, so the key idea, I said that a derived orbifold is something like an orbifold and an orbibundle in a section. So one, deform the section, maybe I should say perturb it, so that the singularities of S inverse of 0 are modeled after algebraic varieties. So if you have a point here, there's a group and a representation. If there's another point here, there's a group and a representation. There's the same group and a different representation in the fiber. So that means you can just look at polynomial maps, complex analytic maps, which are equivariant, which basically means map from, equivariant holomorphic maps in that chart from this to this. Okay, well, you can't achieve transversality if they're equivariant, but still, you're in the world of algebraic varieties. You can look at the 0 locus. It will be locally presented, given to you as an algebraic varieties, and then you can apply resolution of singularities. Okay, so this was, the reason, could even think of this is because at some point I was sitting in a lecture of Dan Abramovich, and he was explaining how they now have some good functorial procedure for doing resolution of singularities. And well, if it's good enough, functorial enough, we can just apply it in settings where this is nothing here is algebraic, except for the fact that there is some, finite groups and representations going on. And so you can linear algebra, it certainly fits inside algebraic geometry, and that's all we were doing here. Okay? So I'll put it as a question. Does there exist ring split? If the answer is yes, then that would be wonderful, because then we can go back to these results of the homotopy theorists and say, oh, look, we can produce for you even more categories over complex cobordism, but of course not over complex cobordism, because then we can produce examples over complex cobordism, but then you have to take this Novikov ring, okay, as always in symplectic topology, and they will not always be smooth, because we know that Fukaya categories are not always smooth, but certainly many of them are. Okay, so that's the first problem. Yes.
It's particular to explain why mirror map has integer coefficients. Yeah.
So among the many things that I'm hoping for is that we would eventually have an explanation. But that might be possible to do just here, okay, without going all the way to mu.
Also get like Calabi varieties or defined over.
Yes, yes. But now let me say the next. Was that the next thing on my mind? I have a list. No, so that will come last. I think I have time to say 2 more things. Okay, so I will come to that. So now, great. So it looks like we have some coefficients over which we can do these things. But there's a problem. The problem is one that Maxime dealt with about 30 years ago, maybe, which is that when you think about the Fukaya category in a setting where you have a closed symplectic manifold, even if you are working over the complex number or Q, the thing you realize is that you don't have chain complexes. Okay, you don't start with an ordinary category. So, problem, curvature. Okay, so if you look at the Floer complex of a pair of Lagrangians in some symplectic manifold, where again you don't assume this kind of Weinstein property, then normally this does not have d squared equals 0. Okay, so there's no chain complex, so there's no homology. Well, if there's no homology, there's nothing to lift. But the solution that Maxime found is called, which was then written by, I guess at first they were doing it together, and then so Kontsevich plus Fu cubed. Fukaya, let me just say, since it's not a symplectic, Fukaya, is to realize that, okay, so you start with this thing, it doesn't have the equals 0, but first you should write down the full set of equations, not to just try to write down just the differential. So what there is, in fact, there is a curved A-infinity algebra, or category, let's just say category, which means that each object, each Lagrangian, has an element which is called M0 of L living in its Floer algebra. Okay, and then the equation that you have is not d squared equals 0, but the equation is d squared of some element x equals, I'm just going to be sloppy, m0 times x plus or minus x times m0 plus a bunch of higher order terms. Actually, no, that's all it is. What did I say? This next thing is going to require the higher order terms. Okay, and then there are operations, multiplication, that go beyond multiplication. Here I wrote multiplication. There's higher operations. So what was the, okay, this is not a solution. This is just says, like, this is how to encode all the problems that you face. Okay, so the solution that they had is called bounding cochains. And that is to look for an element B such that d of B equals m0 plus the product B times m0 plus m0 times B plus higher order terms. Okay? Sorry, what?
Maybe B times.
No, sorry. B times B. Yes, thank you. Yep. Okay. Plus higher order terms, which is higher multiplication. Thank you. Okay, so this you can actually try to do this. You can try to do this in the world of spectra, but it's somehow it's not quite the right thing. And the reason that it's not quite the right thing has to do with the fact that this notion already, if you pass from, this notion is very good if you're working over the complex numbers, but already if you try to work over Z, you discover that it's often the case that there's not enough solutions. So already over Z, this may not be a great notion, may not be sufficient, And let me explain by an example, for a quick example, which is that if you look at CP2, complex projective space, inside CP2 there is a 2 torus called the Clifford 2 torus. And we somehow know that all the Floer theory of CP2 should somehow be encoded in this 2 torus, in some sense. But if you look at it over Z, so over Z, there are not enough bounding cochains. Okay, and that has to do, if you look at it, if you kind of go further and think about the Fukaya category over the complex numbers, you realize that what's going on is that there should be 3 interesting, basically bounding cochains, and they're located at the 3 roots of unity. Okay, and only one of them you can find over the integers, and the other ones require, requiring having a root, a solution to x cubed equals 1. Okay, but that's actually not a big deal. But that has a solution. So the solution is to think of these objects as kind of branes supported on the Lagrangian, which are simple, which have rank 1. So you can have higher rank objects. Okay, but if you are looking at higher rank objects, maybe it's better to have a kind of a more formal definition, okay, so that you can prove that everything is representable in a certain type. And the thing that I'm trying to say here is that you can redefine, you can embed category of bounding cochains in the category of modules over the underlying curved A infinity algebra. This is underlying curved A infinity algebra. Now, category of modules over an algebra, that's always a hideous thing because there's so many objects. Okay, you're not really going to control it. You're never going to be able to talk about its K-theory or so on and so forth. But in fact, it's not just there. There is inside of this some category of dualizable modules. Okay, and the bounding cochains live there.
Dualizable in what sense? There's no tensor structure.
Dualizable in the sense that if you, okay, so let me write the module as L. Okay, so this is some left module. Okay, maybe I should make it R. This is a right module. Okay, so you can tensor over A with Hom from R to A over A. This is a left module. Okay, this is a left module, this is a right module. You can tensor them together, and there is a natural map from this to Hom of module from R to R over A. And dualizable means that this is an equivalence. And you have to do everything correctly because everything is over some Navi covering. You have to do some completions. But let me not do the completion. There's only one way to do this correctly that gives rise to this. Okay, so this definition, this formalism makes sense even in world of curved A infinity algebras, and you can then just do the same thing here. Now, why did I go through this detour? I went through this detour precisely to tell you that you can do the same thing. This has been a mystery for a very long time. How in the world are we going to do curved A infinity categories when we're doing spectral stuff? And the answer is, okay, so first I want to give some words. So I expect that this will be written, hopefully, so expect that this will appear in work with Groman, UL Groman and Umut Varulgunesh. Okay, so we're writing something. I don't know if it will have this or it will have to be the next version. Hopefully it will have this. Okay, so now, so now you can do the same thing. Can do the same with Bordism. Okay, so there is some, I don't want to use the word curved A infinity algebra or curved A infinity category because that suggests something where you write down a bunch of equations. Okay, but what you do basically, and this is why I talk, when I say Bordism, I write this symbol. Okay? There is a homotopy theorist in the room. They're probably saying, why is this very old-fashioned person writing this instead of writing what we write, which is they always write this. Okay? So this is some object of the world of homotopy theory constructed from Grassmannians. It happens to be equivalent to this. But in here, there's no manifold. They're all hiding. Manifolds are here, and then there's some equivalence, which is proved probably not in this room, because I assume this room didn't exist at the time, but at this institution by Tom, that these two things give you the same answer. Okay, but I don't want this guy. I mean, I nothing against it, but it's not what actually gives rise to what we want. This is the thing that gives the structure we want. So if you think in terms of Bordism, you can just take all the moduli spaces of holomorphic disks and the structure that they satisfy in terms of boundary, okay, and that defines some notion which you could call a curved A infinity category over IE. You can formulate notion of curved A infinity category, okay, by literally just looking at what structure the moduli spaces have. Okay, it turns.
But do you use Lagrangian submanifolds or what?
So you can define it abstractly. So abstractly, a curved infinity category is a collection of manifolds with corners, which satisfying certain, so that there's a product map between them, and then blah blah blah. Okay. Now, if you look at Lagrangians inside the symplectic manifold, it will produce such a thing. But I think it is important to have an abstract definition that says there is a world. In fact, the collection of curved A infinity categories forms a two-category. Okay, but that's the case even in this world of Bordism. So we can formulate this and a notion of module.
So this makes sense. It doesn't make sense over the sphere, right?
Yes. Everything makes sense. So I wrote here frame Bordism, complex Bordism, oriented Bordism. Every single one of these things has a notion of a curved A infinity category. It is exactly the same notion in each case, except you go and you say, what structure does the tangent space of my manifolds have? Or more precisely, my orbifolds. Okay? It really is you just add the adjective at the front. Of course, to keep track of the structure of the tangent space, there's some notation you have to set up. But conceptually, it's the same thing. You can also do spin if you like spin, whatever you want. And the notion of module also makes sense.
Could you use any spectrum? I mean, if you have a spectrum.
So the short answer can be yes, because I could reinterpret the spectrum as some kind of manifolds which are oriented with spectrum. Okay.
Without reinterpreting it.
I mean, my guess is that it would be very hard technical task to do so, because.
You just use this like with this Richard Sarkar other
Yeah. So again, my guess is that it would become hard when you try to think about curvature, because somehow there are some equations that need to hold, and it just feels very unnatural. The other thing is I know of no examples. So I much prefer to develop it this way because it makes transparent what comes out of Floer theory.
If you take a general deformation of one of these guys,
yes,
of an uncurved thing,
yes,
you should get curved deformation.
Well, we can talk, but again, deformation theory is kind of a very hard thing to do already away from characteristic zero. So I don't think of it in terms of deformation. I think of it as I look at the category of modules and I see if there's any objects there. Okay, I only have 4 minutes left. So I want to get to the last topic, which is, this is all very nice, but since the beginning, in fact, since I mentioned that result over there, I've been working entirely in the world of non-commutative geometry. Okay. Now, of course, we know we now have many examples of homological mirror symmetry where we say one side is some symplectic manifold and the other side is some non-commutative thing. But it would be very nice if there is some commutative underlying thing. So, how to get commutative examples. So the issue here is that basically nobody is out here to help you. Yeah? So if you are working over FP or whatever, you can just write some equations and ask yourself, does this define a smooth variety over whatever coefficients I'm working with? But you can't write equations. So there are very sparse examples of varieties over the sphere spectrum or over complex Bordism, sparse examples of varieties over let's just say Bordism spectra. And so first of all, how would you define them? So Lurie has an approach which is very congenial to what we're doing, which is basically you can formulate them as some kind of symmetric monoidal categories satisfying a nice property. Okay? So what is happening here? What is happening is that the difference between the derived category of coherent sheaf and an arbitrary kind of DG category is that the derived category of coherent sheaves has a tensor product, okay, which is commutative tensor product. Now, of course, not everything that has a commutative tensor product is going to come from an algebraic variety, but if I give you the derived category of coherent sheaves together with its commutative tensor product, then you can recover the variety. Okay? Because you basically look for the structure sheaf, which is the unit, and then once you have the structure sheaf, you can look for the points, and then you can just recover the variety itself from that. Okay, so these are formulated, so can be formulated as categories with commutative, with tensor product that is commutative. But now, you need examples. Now let's go back to where we started. The idea is to take mirror symmetry and see whether we can lift it, which means that we have some variety, let's say over Fp, okay? And we have some mirror of it, which is some symplectic manifold. And now we're asking whether that variety lifts so that we can do an enhanced version of mirror symmetry. But a long time ago, not so long ago, but anyway, about 20 years ago, people realized that you can take the tensor product on coherent sheaves and therefore translate it into some construction on the Fukaya category. So if X is mirror to M, and this is a variety, and this is symplectic, then the tensor product on X corresponds to a Lagrangian gamma tensor that lives in M cubed. Okay? So I'm running over, but I will stop in 2 minutes. Okay? So there is some Lagrangian here. Now, in principle, actually, it's not a Lagrangian, it's some object of the Fukaya category. Okay? But you can ask yourself whether, once you have it, if you can describe it, you can ask whether it itself lifts to whatever your Bordism theory, whatever your ring spectrum is. Okay? So we can ask if a tensor defines an object of the Fukaya category with Bordism coefficients. Okay? And the last thing I will say is a theorem that's just, so this is joint with Bottman and mu. This is 24. It was posted on the archive yesterday. And it says that if M is K3 surface, more precisely K3 surface mapping to S2 by a map that has 24 singular points, okay? Then gamma tensor lifts to complex cobordism. Okay. So in fact, there's some missing stuff here. I'm going to say plus epsilon, or depend exactly how you think about it, which means that what we do is we think about what Lagrangian corresponds to tensor product. We make sure that it is immersed, which is the most difficult part, and that it has double points are completely controlled. We completely understand its topology. Once you do that, there's one remaining question, which is you have to check that it's not obstructed. Back to this problem here. You have to make sure that it doesn't bound holomorphic curves that cause some problem. But it turns out that in this case you can do it. And I think one way to do it will be in Mu's thesis, where she uses basically this hyperkähler trick. There are other ways to do it that are more complicated, but that's probably going to be the nicest way to do it. And so now we at least have some, if you assemble everything I said and all the things that I promised you that haven't actually appeared, then we would have an interesting mirror family to K3 surfaces that is actually defined over, complex cobordism ring, but once again, with this Novikov parameter. Okay, thank you.
Questions?
Yeah, in the last theorem, so does this mean that the mirror of this K3, if it was defined over FP originally, it will lead to at least the tensor product will lead to the...
Yeah, this is exactly what this is supposed to give us, yes. Now, if you go around and ask, the people whose job it is to think about these things, they will not be completely shocked. I will say one thing, which is toric varieties lift to the sphere spectrum. Okay, so toric varieties themselves lift, and then when we have these K3, when we study mirror symmetry in these toy cases, we get these toroidal degenerations. Okay, it's a really hard problem to know whether the smoothing of the toroidal degenerations actually makes sense over a given field. Okay, I'm not saying it's an easy thing, but it's not shocking because it says the fiber over zero, we know it exists over the sphere spectrum. The real question is, can you extend? And by the way, the fiber over zero can be attacked by this Weinstein problem. Okay, so it's about the smoothing problem, and I know no method of doing it. I mean, they normally use obstruction theory. It may work in this case, but eventually it's going to stop working. And this is some purely symplectic method to tell you that you can solve the problem. Yes, Maxime.
Yeah, actually I have a little suggestion. Yeah, sure. Yeah, first of all, it's a real integrable systems, yeah, through this language. But then addition law,
that's exactly what it is.
Yeah. But then I get the suggestion several years ago, should start not from smooth Lagrangian, but single Lagrangian set to get this local Fukaya category, and then the information should be defined over this Bordism rings, and then it get speak about curved models and construct curved model without smoothing your variety in a sense. Yeah, that should be right. Canonical procedure.
Yes.
And the second thing, here you get model of K3 only cusp formal neighborhood of cusp of model space.
Of course.
The big question is the full model space. Yeah.
Right. I mean, of course, the answer is that, over these rings, we shouldn't expect that there are so many things that are defined away from the cusp, because there are not so many smooth algebraic varieties over Z.
No, but if you consider modular space of K3 surface, it's to the base and then get universal guy. Yeah.
Yes. This is what I want to say is that in some sense, this is what Lurie did for elliptic curves, right? Yeah. So now you could imagine the question of doing it for K3s and attacking it using mirror symmetry methods. Absolutely.
Yes.
A question: in which case complex K-theory helps here?
In which case, what? Can you? Why complex K-theory? Oh no, I didn't say complex K-theory. I said complex cobordism.
Okay.
Oh, here. Why did I put complex K-theory at some point? Basically because this is the only case. So if you take the Fukaya category and you decategorify it, in some sense you get quantum cohomology. Okay, so the analog for K-theory is understood well enough that there are some computations. People have done computations of quantum K-theory. Okay, nobody else. There's none of these other, rings down here, or for no other ring do we actually have some interesting computations of quantum, whatever, Bordism or something like that. But K-theory we have, so that's why I wanted to point it out, because it could be a reasonable candidate for some non-trivial computation.
Yes. So, a question to your remark about Weinstein. So if you try to proceed as Donatra Pardon's building on, you know something for Weinstein domain, and you can try to. I mean that it lifts to omega phi.
Yeah. So the hardest statement is not the lifting. I mean, the lifting is in some sense automatic from once the theory is set up. The hard thing statement is the smoothness. Okay, but the smoothness you follow what they did. They proved some method to basically say that there is some. That whatever you have these cocores, and then you can use them to they generate, and once you localize at them, then everything goes to zero. That argument is relatively formal and will work in this case as well. I mean, I have every expectation. Again, I'm not claiming a theorem there.
Other questions? Yes.
So what's the meaning of the tensor, gamma tensor?
So this is what Maxime was trying to, he said in a few words what it is. So in this case, so you take the K3 surface, it fibers in tori over S2. Okay, there's some 24 singularities, that's why I said make this generic. Okay, then you can do there is an addition law on all the fibers. There's an addition law on the smooth fibers, but on the singular fibers, you have to figure out what to do. So what's actually proved in this paper, which is a very short paper, which you can look at in the archive again, is that actually the graph of the addition law, if you take its closure, you get something immersed, and there is one double point of the immersion for every critical point of this projection map. It's extremely explicit. It's some, very nice phenomenon. I asked around for months the people whose job it is to think about addition law, like, Arinkin, okay, about whether they knew this fact. And they said the closure of the graph of the addition law, or something like that, is Cohen-Macaulay. So that seemed to be all they noticed. They never actually tried to compute in local model what happens. And when you compute, what you get is the small resolution of an ODP singularity. Okay, so there's this conifold singularity. It has a small resolution. That is exactly what appears in the as a topology of the graph.
That's very well known.
Yeah, but where? Who? You will tell me later. I looked, but again,
it's in our paper with Ron, for example.
Okay, so that's why I asked the wrong person.
All right, let's thank Mohammed again.